So good morning. I hope you're doing okay. Are you? Okay. Well, we're approaching the end of the semester. We're not done yet. We are still trying to talk about MBPT. So today we'll continue doing this. As you remember, last time we discussed the fourth order correction to the energy. And we noticed that there is a mathematical cancellation of the disconnected diagrams originating from the principal term of it with the renormalization terms. Okay? So in other words, we anticipate that a similar cancellation will occur in every order. And that means that if I write a correction in an arbitrary order, k0 n plus 1 here, or delta e 0 n plus 1 if you like, then all we need to do is to consider diagrams that originate from the principal term, diagrams that have no external lines, that originate from a principal term, and that are connected. Okay? In other words, there's already a big benefit. We don't have to consider renormalization terms at all, and we don't even have to draw all diagrams from the principal term. Okay? So this is already one of the aspects of the linked cluster theorem, which we'll prove. Well, then after this, after discovering or after observing this fact in the fourth order, we started analyzing the wave function corrections. Okay, trying to see what kinds of cancellations may occur there. We started with the first two orders. Well, we couldn't find anything interesting about cancellation in those orders. So we analyzed their physical content, the doubles, the triples, the quadruples, where they show up and all that. But we couldn't find any cancellations, and that suggested that we need to go to higher orders, and we started analyzing the third order correction to the wave function. Okay, and we demonstrated, at least so far, the following. We demonstrated that among various terms of the third order correction originating from the principal term of it, we have, this is principal term, we have connected diagrams. Okay, I'll start maybe writing them examples here. So one of the diagrams that we considered was something looking like that. Okay. Of course, you can draw a lot more. You can look at, say, a diagram. This diagram is a connected diagram that maximizes the number of external lines. But of course, we can look at other cases. Say, suppose I connect these two vertices with two lines rather than one here. Well, then I'm left with two, and then I have one here. And of course, you can go on and on and on. We noticed that we can group these connected diagrams using time versions of the second kind, but right now this is not really critical to us. What turned out to be more interesting was an observation that we also have various disconnected diagrams. Okay, so I'll continue writing here. That we found quite a few disconnected diagrams. I'm going to use the symbol DC. Okay, to emphasize that I'm picking up disconnected diagrams out of the principal term, this operator product here, all acting on phi0, meaning having external lines. Okay, and those disconnected diagrams can be obtained in two different ways. One possibility is to simply keep three perturbation vertices separate. Okay, so if this is okay, I should probably say that this is this DC group. Okay, so that's one possibility of having a disconnected wave function diagram. Okay, and then we have the whole category of diagrams where two of the three perturbation vertices are connected. Okay, and the other one is kept separate. So those are where situation where we connect, say, two of the three vertices with one line and keep the other V vertex, perturbation vertex separate. Here I'm using V, to represent the W. Of course, we could repeat this analysis with the Q vertices. We're not going to do this. Looking at the V is enough for now. Okay. Then we could have a situation where we connect two of the three vertices with two lines, keeping the third vertex separate. Okay. So maybe I'll put a semicolon here to separate. But here I'll start putting commas. Okay. Then we could have a situation where we connect two of the three vertices with three lines. Okay, and then we keep the third vertex separate. And then we could also connect two of the three vertices with four lines, and then keep the third vertex separate. Okay, comma here, I guess, comma here. Okay, so this is what we proved, and then we showed that along with, for example, this group, we would also have to consider all time versions of the first kind, okay, obtained by simply permuting perturbation vertices along the time axis without changing the orientations of lines, okay, or the particle Hall character of the line. So I will say here that in addition to all of this, we should say plus TV1. You remember the acronym, time versions of the first kind for each of these diagrams, okay? So that's where we are right now, and then, thanks to Cole, we noticed that among our disconnected diagrams, there is one category which we haven't seen before, completely new to us right now, and it's a category related to this diagram, okay? A diagram which is disconnected, but in such a way that one of the two pieces in it is completely closed. We call that piece a vacuum piece, a piece where all the lines in it are fully contracted. Okay? So let's look at this diagram in greater, with some sort of, in detail. Okay? I said last time that this is an example of the unlinked diagram. Okay? So we introduced a new term, unlinked diagrams. So this is unlinked. And then all of this implies that we found two unlinked diagrams among all the disconnected diagrams in the wave function correction. Okay? This is, so I'm redrawing the one that you see on the top blackboard. And then we have also its companion, which is simply a time version of it, obtained by moving this vertex behind the bottom vertex. Okay? So we have these two. Okay? As I also emphasized, just like for every other disconnected diagram that we are really having here all time versions of the first kind, because if you try to form a third possibility, which is taking this piece and write it here, you would end up with dangerous denominators, okay, which are not allowed in MBPT, meaning that those are indeed all time versions, okay? Of the first kind. Of this particular piece, okay? All right. So then, maybe what I'll do, I'll also emphasize where the resolvents are. So resolvent is here, resolvent is here, resolvent is here. We have resolvent here, here, and here, okay? They all come in the first power. So I'll emphasize this as well, and that's because these two diagrams originate from the principal term, okay? And we would like to now understand the role of these diagrams in our calculations, okay? Before I do this, I'll go back to the top blackboard, okay? And I sort of say that, okay, so for the principal term, we identified connected and disconnected diagrams, but of course, there is also a renormalization term in this expression, okay? Which looks as phi 0 W R0 W phi 0, okay, times R0 squared W phi 0, okay? We haven't done much about the renormalization term, but we have to remember that it's there. So, and this of course is second order correction to the energy as a reminder. Okay, so we have this part which originates from the principal pair, okay, and then here we have a renormalization there, okay? And now we would like to see what is the role of the unlinked diagrams in our considerations. Before I do this, let me talk a little bit more about unlinked diagrams, okay? And that also means, let me talk a little bit about the linked ones. So an unlinked diagram in general, as I already said last time, is defined as a disconnected diagram. So please remember the word disconnected in the definition. A disconnected diagram that contains at least one vacuum piece. Okay? Can have more, but at least one. By that I mean a piece that is completely closed. Okay. Now that by negating this definition, we can say that the linked diagram is a diagram that does not contain vacuum pieces. Okay? So so now as you can see, we have four terms characterizing diagrams that we are using. We have connected diagrams, we have disconnected diagrams. This is something we introduced a long time ago. Now we have also linked diagrams and unlinked diagrams. And I think it is good to take a little breath and understand the relationship among these four categories, okay? To make sure that we have a good understanding of them. Alright, so let me maybe create a little table that emphasizes these relationships, okay? So in general, if I have so let's write here connected diagrams, and here let's have disconnected diagrams, which we abbreviate here by C, and for disconnected we use the symbol DC. DC, okay? Not AC, DC, but C and DC. All right. Okay. Now we are saying that there are also linked and unlinked diagrams. Okay, well, first of all, connected diagrams are always linked. Okay, so when I write here, what I'm going to do now here, I'm going to say that every connected diagram is linked. Connected diagrams can have, I will write here some examples. Connected diagrams may be diagrams that have some external lines. Well, that might be one good example. Okay, it says connected, has external lines. It is among our diagrams, actually it was there, when we looked at the second order. Okay, but also you can have connected diagrams that have no external lines that contribute to the energy. Well, you may then say, well, wait a minute, you just said, right, that unlinked diagrams are diagrams that contain vacuum pieces. And I say that this one is linked. Well, it is linked because remember, when you say unlinked, you also say disconnected. Okay? So a connected diagram with no external lines, it is still linked. Because all we have is one piece. Okay? In order for a diagram to become unlinked, it has to be disconnected and contain such pieces. Okay? Pieces that have no external lines. Okay? So this means that if I look at disconnected diagrams then, I may have two types of them. We can have linked diagrams here. And an example of a linked disconnected diagram would be, well, we have plenty of them on our blackboard, so I'm going to just pick up one. Okay, you can have, say, one piece and another piece, say the V, okay? This is disconnected, obviously, and it has external lines, okay? In both pieces, meaning that none of the two pieces are closed, okay? That means linked. But we can also have unlinked diagrams, that disconnected unlinked diagrams, and an example would be, of course, what we have here. This is exactly the situation that we are discussing when we say unlinked. I have, say, I have one vacuum piece, for example, and one piece with external lines, okay? That's just an example. Please remember, I can make it really, this is a huge variety. We can have, the vacuum piece can have more vertices, and you can have more than two pieces in a disconnected diagram, okay? As long as you have a disconnected diagram with at least one vacuum piece, you are in the unlinked category. Now, since I have to use symbols in my manipulations, I will use abbreviations. So for the connected, disconnected, we say CDC, respectively. For linked, I will say L. And for unlinked, I'll say UL. Okay? And I'll stick with this notation until the end of the semester. Okay? So please remember about it too. So, connected is always linked, to summarize. Disconnected can be linked or not linked. Okay? You can also present this in a different way, which I think is useful. It's useful to sort of look at these relationships, so when we talk about it, it's all clear. Okay? So I can write it in this way. We learned out that connected means linked, and we've learned that disconnected means linked or unlinked. Okay, so that's a different presentation of the previous diagram. Okay, and it is good to look at it in this way because you can also read it backwards or in reverse. So in other words, if you have a linked diagram, it can be connected or disconnected. But an unlinked diagram is always disconnected. Okay? So that's how these relationships go. Please remember that. Okay, so then let's go back to our third order considerations. So if I look at the top formula there, or the second line, really, you can see that we have, in the third order, we have connected diagrams, which are, according to these considerations, linked. We have disconnected diagrams which split into linked and unlinked categories, and then we have a renormalization there. Okay? So let's write the corresponding formula for the third order then. So what do we have? I'm going to be now a little bit more detailed compared to the previous expression. Okay? So we have connected diagrams from the principal term. Okay? We have disconnected but linked, so I'm going to use both symbols. DC means disconnected, L means linked from the principal term, okay, defined here by these braces. Active Phi0 tells you all the lines going to the left, okay, and then we also have unlinked disconnected diagrams. Okay? But you see here, I will not say disconnected and unlinked, because now I am saying too much. Unlinked is always disconnected, so all I need to say is unlinked. Is this clear? All I need to say is unlinked. I don't have to say DC because it is DC. Okay? So we have connected, disconnected, linked, and unlinked. All coming from the principal term. Look at how rich that principal term now is. And then, of course, we have to subtract the renormalization term. So I'm going to copy from the other blackboard. We have Phi0 W R0 W times square of the resolvent W Phi0. Okay? So now we would like to see what happens with unlinked diagrams and the renormalization term in this expression. Okay? So now I'm going to perform an analysis similar to what I did when I was cancelling diagrams in the energy. Okay? So let me bring those unlinked diagrams. I'm here, Nicole, maybe for a second. I'm going to redraw these diagrams once again, but this time I'll work on details of these diagrams, really trying to calculate them. Okay? So going back to this blackboard. What we have is this. The first of the two unlinked diagrams that we have has this structure of vertices. The second one has that one. Okay? As I already said, our denominators are formed by slicing lines, as I'm showing now with the blue. They are all these denominators come in the first power, because all of this originates from the principal term. I'm going to now add arrows in both diagrams so we can really analyze them in detail. I'll also actually label lines A, I, B, J, CKDL, and I'll do the same thing here. AIBJ CKDL, okay? So IJKL for holes, ABCD for particles, okay? And I will now try to add this up, okay? Now, as in the case of the energy expressions that we considered last time, you can see that the numerator part of each of these two diagrams numerator parts of each of these two diagrams are the same. Because, the numerator is the product of the weight. Weight is 1 over 4 here times 1 over 4 here. That's 1 over 16. You see the same thing here, okay? Signs will be the same if you expand these diagrams using Brandeis. You're, of course, going to read the same signs. The matrix elements, the scalar part, will be also the same because it's going to be just the product of the 3 anti-symmetrized vertices. Okay? So that's still all the same. But there's one more element compared to energy, namely the operator part. But the operator parts are also the same. It's obvious, right? We have the X-dagger express associated with the KC and LD open paths if you go into the random mode. Okay? So where is the difference? The difference is once again only the denominators. Okay? They can be either obtained from lines of the bottom part, top part, or both parts. So just like we did before, I'm going to call the denominator part originating from the top part A. So it's epsilon I minus epsilon A plus epsilon J minus epsilon B. Okay? Let me use red. Maybe this time to emphasize. So this is the A part of the denominator. Okay? And then B will be part that originates from the bottom piece. So epsilon K minus epsilon C plus epsilon L minus epsilon D. Okay? Meaning this part. That's a B. Okay? And then N will be, once again, the numerator part. Okay? So I'll use a capital N just like I did before. So what is then the formula for these two diagrams? Well, it is N over. In the first diagram, I'm slicing first lines that are called here B. Okay, the B lines forming that part of the denominator. Then I have A plus B, and then I have B again. That's how the first diagram looks like with these definitions. Okay, and N being the numerator. Okay. Which has, weights, scalars, signs, and the operator parts. Okay. And then, of course, you have to sum it over A, B, C, D, I, J, K, L. I'm not going to do that at all. That's obvious, right? And then the second diagram, if we use the same notation, has the following form, the following structure. Numerator over B, that's the B for the denominator. Then you have A plus B, and then you have A. Okay, because now we're slicing, in this place, we're slicing lines that I call A here. So you can, of course, add this up once again. You end up with N over B times A plus B. And B times A plus B is common. Then we end up with 1 over B plus 1 over A. 1 over B plus 1 over A is A plus B over A times B. Okay? The A plus B here will cancel the A plus B here. And you end up with N over AB squared. So you, again, are able to factorize our denominators. The long ones become a product of short ones. Okay? And now A relates to the lines of the vacuum piece. Okay? So we end up with a vacuum piece with all lines in it. Okay? The AI, if you like, BJ. Okay? Sliced in this way. Okay? So those are the A, maybe again, I'll try to copy all the notation. That's what we get here. Okay? Times the bottom piece, treated now as a separate diagram, with square of the denominator. Okay? Well, square of the denominator, so here you're going to have, I'm going to say square of the denominator, so it's B squared. Okay? I'm going to mark the lines. So you have CKDL, and we're slicing it. When we start reading the denominator, we slice it with a 2, meaning that here we have square of the denominator. Now if you now say what it is algebraically, what we end up with here is the product of. The first diagram represents the expectation value of perturbation R0, perturbation phi0. Okay? Expectation value of W, R0, W. Well, in principle, I'm using here V vertices, so it's Vn, R0, Vn. But you could do the same with the Q, and you would end up with the same type of expression. And then the second part is the wave function, actually, piece, which has square of the resolvent in it. Okay? So it is R0 squared W phi 0. Okay? If you now look carefully at our expressions, the one specifically at top, this one here, okay, you can see that we just produced the renormalization term of the third order, and there is a perfect cancellation. So I'm going to flip these. Two blackboards. We just demonstrated that there is a mathematical cancellation of this unlinked piece from the principal term and the renormalization term, because they come with opposite signs, and you end up with connected diagrams and disconnected linked. But as I said, connected is linked. So what you're looking here at are connected linked and disconnected linked, or, turn it around, linked diagrams which are either connected or disconnected, means all of them. All linked, okay? Because every linked diagram is either connected or disconnected. Okay? So in other words, we just demonstrated a magnificent result that all that is left from the third order connection to the wave function are the linked diagrams from the principal there, R0W cubed with an L here. Okay? So that means that we can anticipate the following result. We can anticipate that a similar cancellation happens in higher orders. Okay? And this means that we may expect anyway, we have some reasons now, that if you write the nth order correction to the wave function, all that you have to consider is the principal term, R0 W to the n, okay, and all that you have to really focus on are linked diagrams from the principal term. You don't even have to worry about the existence of renormalization terms because they are gone from our calculations. So you're drawing a subset of all diagrams from the principal term, subset which is linked. And linked, you know now what it means. Don't draw their diagrams which contain vacuum pieces. Those are not part of the wave function. Okay? So this is really what's coming. This is really the meaning of the linked cluster theorem, which we will prove. Before I do this, I would like you to like us to practice a little bit more, because I'll be proving various things with factorization of denominators, so it's good to practice a bit more, and also have a homework actually related to what I'm going to say now. So I think to serve both purposes, I'll go to the next order just briefly, okay? Because so far as you can see, these cancellations were really kind of, simple, very simple, right? Trivial almost, right? So you may say, well, yeah, maybe this just happens in this order, right? It doesn't happen in other orders, because in other orders these diagrams get so complicated that it's hard to factorize the denominators when you go to more vertices. So let's sort of convince ourselves that indeed, even when you get fancy with higher orders, cancellations still occur, okay? So I will use, as an example now, our next example, I'll use fourth order correction to the wave function, okay? And I will focus on the principal term of it, which is R0W to the fourth, okay? And I will really not now consider all the connected diagrams and all the disconnected linked diagrams, because we know that, at least we anticipate now, that they will survive. So the linked diagrams will survive. So I will simply specifically look at the unlinked diagrams, okay? Because that's the interesting part, which we hope cancels the renormalization terms, okay? So I'm going to focus on the unlinked part of the principal term in the fourth order, okay? And just like in the previous considerations, I will just focus on the two-body part of our perturbation, because that's the only part that survives when you use artifact references, and that is typically also the dominant part. Okay? Alright. Let me clean this blackboard so I have a little bit more space. So let's now, and this is a good exercise because it also introduces elements of the proof of the so-called factorization lemma, which will be part of the bigger proof of the linked theorem. Okay. So when I look at these unlinked diagrams in fourth order, coming from the principal term, we have now 4 vertices. So you can think that there will be 2 categories of unlinked diagrams. There will be unlinked diagrams where 2 of the 4 vertices are fully connected to form a closed piece. Okay? And there will be also a new sort of example for us, namely the situation where 3 vertices form a closed piece, and then the fourth vertex will be separate. So let's look at this in greater detail. So what do we have? We will have the following. We'll have, as I said, we'll have situation where 2 of the 4 vertices are fully connected, forming a vacuum piece, and the other 2, well, are doing whatever they want to do. So they can be kept separate, okay, like this. All right. You can have a situation where, maybe I'll start drawing them below. So that's one possibility. We can have 2 of the 4 vertices fully connected, forming the closed piece. Okay, and then the other 2 connected with a single line. Okay, in the previous example I kept them disconnected. Then we can have the same vacuum piece and the no, I want to draw it differently. So let's do it this way. So we have, and the remaining 2 are connected with 2 lines. Okay? And then we can have the same vacuum piece, and now the remaining 2 connected 3 lines. And then, of course, it may be tempting, if you just follow the logic of what I'm doing, is to form the next example, which would be these 2 pieces and those 2 pieces fully connected. But you can't do it. Well, here for 2 reasons. But one reason is obvious. You don't have external lines there. But in wave function, we have to have external lines. So we are not really going to consider cases where all lines are connected, no matter how they look like. Okay? So I don't have more in this category. Of course, with each of these pieces, we have all time versions of the first kind. Okay, because we already learned by looking at the previous orders that these disconnected diagrams come in groups, okay, related by time versions of the first kind. So in other words, this diagram here will have all of its time versions of the first kind, where you simply start permuting, moving these vertices around, okay, and if you can apply the same to these, okay. So, you'll have time versions of the first kind here, okay? You'll have time versions of the first kind here, and you'll have time versions of the first kind here, okay? To just make sure that you obtain all diagrams. And of course, if those are skeletons, if you want to go to real diagrams, you still have to put arrows and do that. But, this is not important right now. What is important right now is that we have, those are all categories of skeletons, okay, that are obtained by forming a vacuum piece from 2 vertices. But there is one more. That's your homework. Okay? You can also consider a case where you form a vacuum piece from 3 vertices, something that looks like this, and then you have the 4th perturbation vertex kept separate. Okay? And once again, you have to consider all time versions of the first kind for it. Okay? So maybe, once again, I will, well, actually, I don't think no, let's do this. Let's do this. So what do we have here? Of course, we always have to remember, let me do it nicely. Always remember, you remember when I was talking to you before about how to draw diagrams, always end these lines on a, the same. You can see now why this is so important, because if you don't, right, you may not read them entirely correctly. So this is safer, okay? So if you look at the denominators, let's sort of make sure. So we have denominators here arranged in this way by slicing these diagrams with 4 resolvents, all coming in the first hour. And you have to, well, of course, for time versions, they will be arranged differently, but you have to do this as well. Let me also nicely present this one. So we have our resolvents, make lines long enough. Resolvents here and here. That's your particular problem in your homework. Your resolvents in it, as you see in the homework, the diagram is shown there, go this way. Okay, and then you have to consider all time versions. Okay? Alright, I'll come back to this. Okay, so now what I'm going to do is this. This is how all the unlinked diagrams look like. Okay? Let's now see how they factorize. Can we factorize them? What I'm going to do, I'm going to pick up one representative skeleton. How about if we pick up this one, for example, all right, for our analysis, because you can, you can clearly see that the remaining ones are very similar. Okay, so I'll just start with what I have there, as it looks this way. Okay, and then I will now consider all time versions of the first kind of it. Okay, so that's my blue. Bring those shots here. So the resolvents here are going this way, and then let's look at all time versions in this case. Okay. So time versions are obtained by permuting vertices along the time axis. So my next case will be take this vertex, move it between the bottom two. Right. So if I use the numbering 1, 2, 3, 4 for the vertices, right now it's 1, 2, 3, 4, but I can take the 2 and move it between 3 and 4. Okay, that's my next time version. So always do it systematically. Okay, so I will have something like this. Okay, so you can see now this is where 1 was. This is now 2. You can see it went to a different location. This is 3 and this is 4. Okay, I can then continue and take this and move it to the end. Okay. So now you have, a situation such that this top part kind of encompasses the bottom part. Okay. Then you will also have, now you can do the next one, next step, which is take this vacuum piece and move it between 3 and 4. Okay. That's the next logical category. So I will make 3 and 4, the bottom piece sort of a bit longer, stretch it a little bit, so that you can see these things better. Okay, and the top piece will be right between the bottom two. And the final case is take this, stretch it here. Okay, so you will have okay, this. All right. Okay. Well, of course, if you think logically about what I'm doing, all these permutations, you can think, well, maybe I should also take this vertex and move it outside. Well, you can't do it because that will create a dangerous denominator situation once again. So we are not allowed to do this. Okay. So those are all time versions of the first kind for this skeleton. Okay. So let me now mark the resolvent. Okay. They all come in the first power. I'm not going to say it because we are right at the beginning because we know it. Okay. And now let's analyze the denominators. Just like in all the previous cases, I think you're already used to it. The numerator part of each of these 5 skeletons is the same. Okay. because the weights are the same, the signs will be the same, and so on. Of course, you know, in principle, in each case, you have to consider different kinds of line orientations, like for example, two holes, two particles, particle and hole. Okay, so of course, each of these characters represents more. But for each particular type, okay, the weights, the signs, scalars, and the operator parts will be identical. So I'm not going to write these, you know, I'm not going to put arrows anymore. I'll just mark where the denominators are coming from. So, you know, they can come here from the top lines. They can come from the bottom lines of this part. You see there are two denominators now at the bottom, right? So they can come from here, or they can come from the lines that are connecting the two vertices of the bottom piece. So I'm going to call these pieces of the denominator A, B, and C. Okay? What I need to do now is to work out the expression, or you know, for the sum of all these skeletons. Okay? I'm going to of course follow the previous recipes. So n will stand for the numerator. Okay? N is the numerator now. And let's start reading. You can of course help me if you like. So what is the first one in your view? What should I start writing? First denominator. B, that's right. The next one is A plus B, right? The next one is B and then C, perfect. And then, you know, you repeat this for the next. So the next one should be B, then we have A plus B, then we have A plus C, right? And then we have C. Agree? Then the next one, maybe you can dictate again. What should I say? All right. B, then A plus B, right? And then A plus C, perfect. And then A, perfect. Okay. And then there are two more, so maybe I'll write them here. So here we have a numerator part, and then we have the fourth one is over there. So we have B times B and C there first, right? Then we have A plus C, and then we have C, right? And the last one, maybe you can say now. Again, B. Last one. B and C and A plus C and A, okay? That's how this looks like, okay? That's exactly the kind of work you'll be doing in your homework, right? When you write time versions of the diagram shown there, okay? So now, you know, you need to just add this up together. You know, it's good to simply pair them by looking at where the most common elements are, okay? So here you can see that we have, you know, the first term does not seem to have a lot in common with other terms, so you start with, I'm just going to copy it, okay? Then for those two, you can see that B, A plus B, and A plus C is the same both, okay? And then, so you know, we can start writing by saying N over B times A plus B times A plus C. And then you have 1 over C from here, plus 1 over A from here. But 1 over C plus 1 over A is A plus C divided by AC. Is that okay? Right, so that means that A plus C cancels out, and we have already some simplification there. And then when you look at the last pair, okay, you can see once again that they also have they have a lot in common. They have B, C, and A plus C in common, okay, here and here. And then we have 1 over C plus 1 over A, which is A plus C over AC, okay? Again, there is a cancellation of the A plus C, okay? So now, when you continue, maybe I'll use color, you can see that these two can still be combined together. Okay? You know, what you have here is B and A plus B, okay? And as a matter of fact, also C are the same both, right? When you cancel A plus C, it's gone. So you can see that here, B times A plus B is the same, and also C is the same when I combine these two. Okay? Can you see? Alright, so that means that these two can be combined as follows. We have N over first what's in common. So B times A plus B times C. And then you end up with 1 over B here and 1 over A here. But 1 over B plus 1 over A is A plus B over AB. Okay? So we end up with A plus B over AB. Is this clear? I'm trying to go quickly through it because it's really trivial algebra. Okay? Is this all clear to you? Okay. All right. And then, so that's what happens with those two. And then this one, already is pretty clean. So I don't have to do much about it. You have a numerator over, if you look carefully at it, you have A, then you have B and C squared. So it gets a very interesting structure, A, B, C squared. Now, in the first term, I can still cancel the long denominator, A plus B. And I am done. Now, I have now N over, you have A, B squared C, plus N over A, B, C squared. Okay? Well, let's interpret this result, which I'll do perhaps, maybe I'll still have a little space here, so I'm going to put this up so that you can see it actually nicely. And let's just go back and see what then we end up with here. So after adding all these skeletons, you see I end up with a product of the vacuum piece, okay? If you look at the first term, this one here, A is in the first power, so I'm slicing it with the solvent in the first power, okay? Then you have B squared C, meaning that you have, with B and C belong to the denominators of the bottom piece, okay? So you end up with times the bottom piece, where B is in the square, meaning that that resolvent here is with a square, and then you have C, that resolvent is in the first power. Okay? But then you have the companion piece there, which is the same numerator, so you end up with the product of the same types of skeletons, except that the denominators will be slightly different. So this one still has A in the first power, okay? So I'm putting first power here. But then we have B, meaning the B lines which are here, okay? Those will come in the first power, and then C is squared now. So that means that lines that are, I called before C, are coming, the denominator for them comes from a square. That means square of the resultant. Now, when you read this, an algebraic form of it, you can see that we have this term is common to both, okay? So what I end up with is phi 0 W. I write W to represent, the perturbation, because I could repeat this for the Q vertices. So it's going to be W R0 W phi 0, which is of course the second order correction to the energy, times, well, there are two terms as you can see. This one is R0 squared W, okay, then R0 W phi 0, okay? This one goes in reverse when it comes to resolvents. It is, okay, the vacuum piece I wrote it outside, and then you have R0 W R0 squared W phi 0, okay? Well, that's what we get, all right, for this particular piece. That is, of course, right now, maybe I should be, maybe, okay, I will actually erase this, because, I'm sorry, this is sort of a little bit not entirely correct. It is what I wanted to say, but not correct. So, right now, what we see, maybe I should say this. There is this common piece, okay, times the two. So please erase what I said. Now, I would like now to summarize what I did, okay? So maybe I'll still keep it down. Oh, let's put it down, actually, and then let me go to the other side of the Bergers, because I don't have much space here. Okay? What I should have said, I was a little bit rushing, is this. I could repeat the same analysis for the other diagrams. That's what I really wanted to say. Okay? You see, they have the same structure. A vacuum piece times the bottom piece. Okay? You can see in these considerations, I never really looked at the nature of the bottom piece in detail. I didn't really care about how many lines are connecting the vertices in there and so on, right? It could be 3, it could be 1, right? It could be none, okay? So if you repeat this for this whole bunch, okay, of these diagrams, this one here, that one, that one, and that one. If you repeat these considerations, okay, for all these diagrams, you will see that they will factorize in the same way as the one we processed. Okay? So you will end up with, okay, if I continue all these, maybe I'll write it here nicely. If I look at all these unlinked diagrams acting on phi 0, the pieces that I marked here, this, and this, they will factorize as a vacuum piece, okay, with the resolvent coming in the first power, just like we have here, okay, times the following. For the first diagram, which is the top blackboard on the left, we have these two vertices with the first resolvent. If you follow this model, you see the first resolvent being equal to a square, the second resolvent being in the first power. So we end up with the first resolvent being with a square, the second resolvent being in the first power. Well, then you also will have a companion piece, which will have 1 here and 2 here. I'll write it a little bit later. Then, if you really continue, you will see that for this diagram, I will end up with this piece, the bottom piece here, with the arrangement of resolvents of the 2-1 type. Okay, so we'll have this, okay, this will be 2, this will be 1. Okay, is this clear to everybody what I'm doing? Okay, now if you look at then this diagram we just did, so it's this vacuum piece times this, alright? So maybe I'll write one more here. Square of the resolvent here, first power here. And then there is also this piece where you end up with vacuum piece times this wave function piece, okay? Which will have again resolvents arranged as square first power, okay? But then, as I said, from our calculations, which we did specifically for this case, okay, you can see that we also have, this situation, right? A vacuum piece of the same kind times the wave function piece with resolvents arranged as R0, R0 squared. Okay? So I'll have to repeat those 4 diagrams with this other arrangement of the resolvents. Okay? So you will have first power of the resolvent in the leftmost position and the second power of the resolvent in the next one, in the next position. Then you will have this diagram with 1, 2 for the powers of the corresponding resolvents. Then this diagram once again with 1, 2. Okay? And finally this one here, where the leftmost resolvent is R0 and the next one is R0, comes with a square. Okay? So you will have this situation. 1, 2. Okay? Now I can close the curly bracket. Okay? So those are, is this clear? Those are all diagrams that we end up with, by adding this piece. So I'm here, let me go for a second. This piece, this piece, this piece, this piece, and all of their time versions of the first kind. If I do that, I end up with this. Well, your role in the homework is to process this one. Do exactly what I did for the example we considered. Consider all time versions of it, and do the factorization of the denominators. Okay, now you know, I hope, how to do it, precisely, because we did it so many times. And you will be able to prove. I'll just show you what you're going to get. Okay, that may be useful. What you're going to add, I'm going to now add it here, will be a product of the vacuum piece, which is this interesting piece containing 3 vertices, okay, with resolvents coming in the first power, okay, times the wave function piece that you have there, which consists of a single perturbation vertex with resolvents with a square in it. Okay? Something like this. Okay. This is how the unlinked diagram, this is what happens to unlinked diagrams when you add all of them together and factorize the corresponding denominators. Okay? Just please make sure that you copy it correctly. I also take a moment to make sure that I didn't mess it up. Okay? I think it looks okay. Now we have to interpret, I was sort of rushing before. Now we have to interpret what we see. Okay. So what I'm going to do now, if you don't mind, I will now erase this because we already are done with all these diagrams. And we'll try to understand what is that we see. Okay? Here. Well, this is obvious. This is an expectation value of V of W R0 W if you use W, if you generalize it to the Q parts of W. Okay? So it's going to be W R0 W and you form an expectation value of it. Okay? Look how cool this is. All these diagrams here. This, and that. Okay? Maybe I'll mark them. Okay, this one, and that one. Those are all possible diagrams obtained from R0 W squared R0 W. Can you see this? There are no other. If I give you two vertices, you will be able to keep them disconnected, connected with one line, connected with two lines, and connected with three lines, right? There is nothing else. So that means that these first four diagrams that I marked with red represent what I will started writing too early. R0 squared, W, R0, W phi 0. That's what they represent. Okay? Now, if you look at the next four, I'm marking in blue, this one, that one, that one, and that one, they also represent all possible diagrams that you can obtain from two vertices, because you have now disconnected, connected with one, connected with two, connected with three, but with different form of the resolvent arrangement. We have R0, R0 squared in each one of them. Okay? So you end up with R0, W, R0 squared, W phi 0. Okay? That's what we have. And then, well, let's look at this one. This is your homework. What is this one? Can you tell me actually what is this one? What should I write for it? Okay, you remember what is it? What is this quantity? By the way? Third order, that's right. It's a third order correction to the energy. Okay? This one actually, as a reminder, it's a second order correction to the energy. Okay? And then what is the next one? What should I say? What should I write? What should I write here? Perfect. Wonderful. R0 squared W phi 0. Okay. If you go back to your lecture notes, you'll see that this is exactly the renormalization term in the fourth order wave function. Okay? This is exactly the renormalization term of psi 04. Okay? Those are renormalization terms of psi 04. Of course, in principle, in psi 04 there is more, but we expect, but there will be the remaining ones will be containing expectation value of a single W, which is 0 in our case because of normal ordering. Okay. So we just demonstrated that. Look, and you can see how fancy that is now. It's not some sort of a simple. This is pretty cool. You really end up with, an analysis which leads to a rich variety of diagrams and then a rich variety of renormalization terms, and we still can cancel them, all of them. Nothing is left. So we then really can anticipate, when you see so much, it doesn't look like this is some sort of a coincidence, right? It shows up over and over again that when you look at the wave function correction in nth order, then you just have to focus on the linked parts of it, because the unlinked parts of the principal term cancel precisely the renormalization terms, okay? So now, of course, that means that right now we are, I guess, ready to go to the proof of linked-Castells theorem. We have now a lot of experience with these expressions, so we should now go there. Before I do this, I would like to discuss a small but extremely important topic of the exclusion principle violating diagrams, okay? So that you can appreciate the nature of the cancellation we are, considering here, okay? So let's have a 5-minute break, okay? And then I'll talk about exclusion principle violating diagrams and their role in the cancellations that we observe, okay? All right. So as I said, 5 minutes, and then we'll resume. Okay. So I got a message from Rachel.
Yeah, I can do extra technique.
You can do this, yeah?
Yeah.
So right now I don't, so we reserve this room from 8 to 12 just to make sure that we have a block, right? And of course I cannot tell right now how many hours this will be. It could be as little as whatever, 90 minutes. It could be maybe 3 hours. In which case we would then break. Would that be okay with you? Then we'll have a break. I'll bring some cookies or something. So you can enjoy it. Okay.
I can do that.
Yeah. Okay. So I'll talk. So let's narrow this down a little bit next week when as I approach the end, I know how much is left more and more precisely. Okay.
Yeah.
Right. Okay. Thank you very much for doing this. Really great. Yeah, and the next thing we need to discuss, I think soon enough, is the final exam. Okay, so I know that we have to do it on Thursday at the earliest. Okay, so would you like to do it on Thursday? Would you like to do it on Friday? Do you have some preferences? Do you would like to split it over into the following week?
Which week are we talking about? May?
I think it's May. There's my phone. May 2nd is Monday, I believe.
Yeah.
So
that week.
So if you want to do it, I'm not insisting, I'm really flexible here, so just tell me what your preference is, because you may have some other exams, so I don't know what else you have to do. But, so May 5th is the earliest we can use, okay? We can go into the 6th, or we can consider, 9th or 10th. I don't remember where it ends. Is it 12? I think it ends sometime in the following week. Yeah. So, of course, if you went to the following week, you would have an extra weekend, I guess, you can say, right? But on the other hand, it's kind of separating you from the actual classes, right? Like some stretch.
So the last day of class is the second. So the last day of class, the last lecture.
The last lecture is on the last lecture will be on the 29th. That's a formal requirement, okay? I will have, we're planning on, because I'm looking at the material and because of the question you're asking, the question you asked me last time, for example, I think that I would like to finish on some sort of a highlight, right? When I finish will be good, we'll cover a lot of material, already, right? But I would like to have one extra lecture where I will go into some depth of couple cluster considerations, okay? Which I may not be able to finish on Friday, simply, okay? And I don't want to rush it so that, write it so fast that nobody can read it, okay? Okay, so, and I agreed with Nicole, she's very kind to us, she'll be recording this as well, so we'll be able to watch it. But of course, in terms of the requirements for the exams, I will not require the knowledge of that lecture. Whatever we happen to talk about on that Monday, May 2nd, okay, I will not include, in all fairness, right, to the, in the final exam. Okay, but I still would like you to be exposed to this knowledge, and maybe some of you will find it useful. Okay, conclusion of this lecture. This is a topic which can go on and on and on forever, right? So I'll have to cut it somewhere. And I think that may be useful for you to see how we derive these equations, what is that we do about solving them, things of that sort, you know, a little bit of details of capital theory. Of course, only in the single reference case, only for the ground state problem, you know, lots of onlys here, you know, I can go through all the richness of it. But at least you'll get a flavor, hopefully, what is that we do. And what we do about the thing that you asked me the other day, namely factorizing diagrams to obtain the computational efficiency. All right. Okay, so you know, in this homework problem that I mentioned, okay, you don't have to, of course, put arrows, you know, don't worry about arrows, there's no need to do that. Of course, you know, this vacuum piece that you have there actually is really 3 diagrams, so you would have to complicate it. Just keep it to the level of skeleton, call these denominators A, B, and C, okay, A, B from the vacuum piece, C for the wave function piece there, okay, and then follow through. Come up with all 5 versions. And it will be your numerator. Use exactly the notation I'm using here, okay? So don't do essentially what I'm doing here with these, you know, A, B, C type notation. So I would, if I were you, I would just call A, B for the denominator. I would use A, B for the denominators in the vacuum piece and then C for the wave function piece and then finish the calculation. Okay? All right. Okay, so you know, I would like you to note, you know, I would like to emphasize now an important point. That is, if you really look at all these considerations that we did, we were able to factorize these diagrams, you know, by adding them together, because our indices are free indices. That is, for example, here, in this example that I have, lines of the bottom piece and lines of the top piece are labeled with independent sets of indices that are running independent of one another, okay? And you are summing them over, but they have no relationship. You have to sum over all indices of the bottom piece, all indices of the top piece, okay? If you go back, for example, you know, otherwise, you know, this factorization would not happen so easily, because you would not end up with a product of this piece treated independent of the other two. Okay, they would be somehow related. So let me talk about this, because that's a very important, that leads to a very important consideration. So let's actually go back for a moment, as you know, as our example. Let's step back and let's look at the third order, okay, which is a little bit easier. And let's look at the unlinked part of it. Oh my God. R0 W cube, okay, phi 0. Nicely here. So we have R0 W cube unlinked phi 0. All right. You know, when you go back to what we did, we looked at the unlinked diagrams in the third order. They were this one and that one. Okay, with the vacuum piece arranged in 2 different ways relative to the bottom piece. Okay, and we demonstrated that when you add them together, and I'll mark the resultants once again using blue lines. So here, here, and here, 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 and here. When we added these two together and factorized the denominators, we proved that this leads to a product of the vacuum piece. Okay, where the resultant is in the first power times the wave function piece, okay, where the resultant is with a square, okay? All right, that's what we did, but if you really pay close attention to what we did, we were able to do this because indices in both pieces are independently summed over, okay? So if I put now arrows, let's actually do that. And let's do it everywhere, okay? You can see that among our diagrams, let's just pick up two lines which have the same orientation. I will pick up this one here. I'm going to call it I. It's a hole. It goes from left to right. And I'm going to pick up this one here, okay? I'm going to call it J for now. I'm not going to label everything else because I'm just going to focus on two lines which have the same orientation. Okay? So you will have I here and J here. And you will then, if you look at where this goes, that I from the top piece will end up here. That index J from the bottom piece will end up here. And the whole point I'm making is that, of course, we are summing over I, we are summing over J, and of course we are summing over all other indices that I'm not showing. Okay? That's the nature of MBPT as we know it. Alright? So that means that there is a summation here, and there is also a summation here. And because these summations are independent, you see you can split the summation over I from the summation over J. You can really separate them. So you can continue saying that this equals the summation over I and other indices of the top piece, okay, times the summation over J and other indices of the bottom piece. So I is here. I will not write all the, okay, I will not mark all the lines, okay, I'm just going to be focusing on two. So I is here, J is here, okay, so we end up with a product like that, where the first, here we have a resolvent in the first power, here we have a resolvent in the second power. You see, and because of the fact that we have these unconstrained indices, and because we are really summing them independent of one another, we can really say that this is simply a product of this times that, because the summation over I here and summation over J here and other indices are independent. And this is exactly why you can claim then that this is an expectation value, okay, of WR0, WP0 times resolvent square W phi0, okay? You would not be able to say this if there was some relationship between I, if there was some relationship between I and J, okay? You can do it because I and J are independent of each other, and you can then split your multiple summation here into the product of summations, okay? That leads to this expression, which is exactly the renormalization term, which then is eliminated. Well, if you really look at this, among these diagrams, if you really pay attention to what indices are, there will be diagrams, you know, when you start summing over all I values and all J values, there will be those situations where I and J turn out to be the same. Like say 1, 1, or 2, 2, or 3, 3 for the occupied indices, right? Those are examples of the so-called exclusion principle. So when I equals J, of course, you know, you could also do, say, A equal B, if I picked up lines which were particles, okay, then those are examples of exclusion principle violating diagrams. Okay, we abbreviate them as EPV. So EPV diagrams are diagrams where indices, okay, of lines with the same orientation and in the same location in the diagram turn out to be the same. Okay? And you can see this can happen here. If I am summing over I and J, I will have among various terms where this I and this J will be the same. And the same for occupied ones. We say that they violate exclusion principle, the poly principle, because, you know, you're using the same index. I mean, the same value of an index. You know, you're saying, say, I equal 1 and J equal 1. That means that you're trying to, remove a particle from spin orbital 1. And you know how to do this in fermions, right? Of course, then we're not violating it. You have to remember, this is just, you know, it happens that those are the terms we have mathematically. We're not violating anything. But, you know, but because these diagrams look this way, people decided to call them EPV diagrams. Diagrams where indices have the same value, okay? So they kind of create an impression as if we're trying to violate the Pauli principle, okay? Well, let's then try to understand. First of all, let's understand, do we violate anything? I said no, but we'll see. Okay, then let's understand where do they come from? Well, you know, we have to rewind a little bit, go back to the beginning of MBPT. Remember in the beginning of MBPT, okay, when I was writing the resolvent, if you go back into your notes, I split the resolvent into n-body pieces, okay, from 1 to n, okay, and initially our resolvent contained a constraint summations. We had phi I1, IN, A1, AN, and then phi I1, IN, A1, AN, okay, divided by minus kappa I1, IN, A1, AN, and then we will have here I1 less than IN, A1 less than AN, okay? Because of course you have to sum over linear independent determinants to avoid repetitions, okay? And then you remember what I did. I said, well, okay, I would prefer to write it differently, so I replaced this by different i's, okay? But I'm not going to rewrite it, but what we did is we replaced this by I1 different than I2, different than IN, okay? I2 is not needed here. Okay? Then we said, let's have these indices A being just different from each other. Of course, that in order to do this, we have to introduce a 1 over n factorial square in front of our resolvent to avoid repetitions. And then we decided on this one important the next step, which is say, well, you know what? Determinants where I1 equals I2 or I1 equals I3 and so on, and the same with A's, all those determinants where I's or A's are the same are zeros. So then we said, well, okay, we don't want to do this. Let's just replace these summations by unconstrained summations over all values of I, that is all occupied, and all values of A, okay, without constraint. So, and it looked at, as some sort of an innocent mathematical trick, right? I mean, all you're doing is, okay, let's, you're trying to say, look, I don't like these constraints, so I'm going to go to unconstrained in this way, and then eventually unconstrained in this way, of course, with 1 over n factorial in front of square, in front of the entire expression, okay? And we did it, so we never had to worry so far about constraints. And of course, as you know, diagrammatic is much easier to deal with diagrams which have free symbols, where you don't have to worry about whether some of them are fixed or whether some of them have some constraints or relationships, okay? And of course, throwing these diagrams where i's or a's can be equal is throwing zeros, but that's exactly also throwing EPV diagrams. Because when you throw these zeros, okay, then what happens? You remember, resolvents enter MBPT expressions. And then you start connecting lines. Okay, when you start connecting lines, you will end up with diagrams that look exactly like this. Where say I and J can happen to be the same. Because there is a resolvent. You see that blue line here? There is a resolvent there where I can be J. And that's the consequence of the fact that we allowed such form of the resolvent, where I is J. Or where in general I's or A's are the same. As I said, at the level of the resolvent, that's just an innocent mathematical trick, just throwing more zeros. Doesn't change anything. But now we are paying the price. Our price is that we have to consider diagrams which have this sort of EPV character. Okay? And you notice, as I said, that having them in our considerations is key. If we didn't have diagrams where I is J, we would not be able to see the cancellation. So let me talk about this now. I don't think I can say a lot more, but I would like you to see this now. Okay? It's an extremely important thing, and I'll try to explain as we go why do I think it's so important. Is this clear what I said so far? It's really tricky. Okay, so imagine, let's, I'm trying to, to rewind. Let's imagine that I start over this MBPT class, okay? And I said, you know what, I don't want to have these unconstrained summations because they do violate Pauli principle. That is, we should all keep i's and a's different, okay? Well, so what if I started from this form of the resolvent, okay, which is 1 over n factorial square, for example, and then i's and a's being different. Well, when you do this, then every resolvent will have that. That is, you will end up, if you start looking at the unlinked diagrams, okay, the same ones that I have in third order. I'm going to focus on this example, okay. In these diagrams, I will not be J. Because I will, and of course that means that other indices will also have to, that for particles line, for example, will also have to be different. Okay? So let's see what happens then. Of course that means that also in the linked part, I will not be J. Everywhere, all over the place, I will never be J. Or in general, occupied or unoccupied indices will always have to be kept different. Because of the form of the resolvent. Okay? Alright. So what do I get? All I need to do is just to repeat what I see on the top blackboard, but let me write it here. I will end up with a sum over these two unlinked diagrams. Okay? Okay? We have, let me continue marking the resolvent. Blue. Okay? So we have one resolvent here, one resolvent here, one here, one here, one here, one here, okay? And I will now mark again the same pair of lines, I here and J here, I here and J here. But now because our resolvent does not allow I indices or indices to be the same, then I have to say that this summation I is not J. You're still summing over I and J, but anytime I becomes J, you throw this term out. That's what this really means. Well, then you can continue our analysis. Okay, do the denominator factorization. So let's see how far we can go. What I'm going to do is this, to facilitate this. I will simply write this term using addition to subtraction. I will add I equal J terms back. Okay, so this will give me summation over all I's and all J's. Okay, so we have then, I have to redraw this. All right, there goes, it's white. Okay, all the resolvents. But now, so now line I here and lines R and J are still where they were. So here I'm summing over all values of I and J and other indices with no constraint, but then, because I say here I different to J, I have to subtract all those cases where I equals J. So let's do the subtraction over, which looks like this. Okay? Maybe I'll write it below. Not be able to squeeze it. So minus the summation, where now I equals J, so I'm going to leave only one of those indices, the I1. Okay, and I have same two diagrams, okay, in terms of the overall shape. Same denominators, of course. But now, when you look at these two lines that I'm picking up on all the time, okay, then this is I and this is now I, because I'm subtracting I equal J. So this is I, this is I. Okay? Let me move this up. Okay, that's where we are. So in other words, if we assume from the very beginning that our resolvent does not allow EPV type terms, then we would end up with the situation that I'm showing up there for the unlinked part. And of course similar for the linked part. Okay. Well, let's read it. The first part, we already know what happens to this one. it's there. It factorizes because indices are unconstrained. So we already proved it. So I'm not going to do this. I'll just write that the first part gives us the renormalization term that we know we would like to eliminate. Okay? That's the first part. But the second part, as you can see, is of the EPV type. Okay? That part is not factorizing in a simple way. So this is EPV. It is EPV because these indices are the same. Okay? What happens to it then? It does factorize, but sort of partly. Okay? What you end up with there is a summation over I. And of course, since you remember this analysis of this factorization never really involved the details of the denominators. We just look at what lines that we're slicing. We're slicing still the same kinds of lines. So you would end up with a product of the vacuum piece and the wave function piece. Okay? Where, the first resolvent here would be, the resolvent in the vacuum piece would be in the first power, resolvent in the wave function piece would be with a square. However, now you have a very interesting case. Because you have I and I here, the top I ends up here. The bottom I ends up in the wave function piece. You see, you can no longer write it as a product. This is sum of products, but not a simple product. Because you have to say, sum is over I equal 1, so you have 1, 1. 2, 2, 2, 3, 3, 3. 1 times 1 plus 2 plus 2 plus 3 plus 3 is not 1 plus 2 plus 3 times 1 plus 2 plus 3. Okay? So you can't factorize it anymore in a clean way. So we end up, so in other words, if we insisted on this form of the MBPT resolvent without EPV terms in it, which are zeros at the level of the resolvent, we would end up with a renormalization term minus EPV diagrams of this sort. Okay? So if you go back to our third order considerations now, okay, and I think that must be the end of our class. Let me just write it. You end up with the following. You end up with R0 W cubed, okay? You end up with the linked diagrams with I different than J, and of course, other differences for other indices that we previously assumed are the same, can be the same, okay? Then you end up with the unlinked part, the unlinked part, which is R0 W cubed, unlinked with I different than J, and then minus the renormalization term, times, so here I'm rewriting it one more time. And as we just demonstrated, when you look at this, you can write it as a renormalization term minus this. So if I take this expression and replace unlinked with I different than J, well, actually going to be 0 here. Please correct me sometimes when I see such things. There's also 0 here. Okay? When you assume that the resolvent does not allow EPV terms, then we have linked diagrams where EPV terms are out. We have unlinked diagrams where EPV terms are out. We have a renormalization. These two cancel out, but not completely. You see what happens? This renormalization term here will cancel that one here, but this will be left over. So you will be left with something, I guess, which is less desired. I guess we can conclude that, right? You end up with the linked diagrams of the principal term, okay, where you do not allow EPV terms. So maybe I'll say here, no EPV, but because you don't want to have EPV diagrams, okay, well then you'll be left with this one, left uncancelled. It's going to be a summation over I, okay, the product of the vacuum and wave function pieces, where I here and I here are the same. So here still resolving the first power, resolving the second power. Okay? Well, that's not really the nice way of writing the Linked-Castle theorem, because you have to now remember that you have to carry over some terms which look like renormalization terms of the EPV term type. Okay? The cancellation is not complete. Do you understand this well enough? Because that's really important. We have to understand how we use Linked-Castle theorem. And you are now learning, and I cannot finish today this, I have a couple of comments, finish next time. We are learning that if you decided to remove EPV terms from the resolvent, you will not end up with a perfect cancellation of unlinked diagrams. You will simply end up with linked diagrams with no EPV and some remainder here that is sort of quasi-factorized, right? But it is not completely factorized and it cannot be eliminated. Okay? So here we have now these sort of EPV type terms. Okay? So then next time what I'll do is I'll show you what really happens when you go deeply into this cancellation stuff. What really happens, that is, what is that we need to do to get rid of this? Okay? How is it happen that we really are able to remove those unlinked EPV terms? Okay? Completely. Alright? Of course you already know more or less. What's going to happen is we have to allow EPV terms. Okay? But what will be interesting here is that we'll be cancelling terms which are not zero. This is not zero. You see, at the level of the resolvent, these EPV terms were zero. You just added zeros to the resolvent. Okay? Now, the consequence is that you end up with terms which are EPV, but they're not zero. This is, you can calculate this matrix element, matrix elements here and here. You end up with some non-zero result. It's not a zero anymore. Okay? So how is it that we can eliminate what is actually non-zero now? Okay? From the calculations. That's going to be the beginning of the next lecture. Okay? A very important thing for the understanding of many-body field. Okay. All right. So thank you very much. Think about the final exam when you want to have it. I'll send you an email reminding about it.